The IEEE 488 standard, or GPIB, defines mechanical, electrical, functional, and bus protocol elements to enable data transfer between similarly defined devices. GPIB was designed for a multiple device local system environment. It stresses remote instrument control, bidirectional asynchronous parallel data transfer, device compatibility, and status and event reporting.
What the GPIB standard does not cover are device-dependent messages. Even though forms of address are standardized, each device may still require a unique set of commands for operation and data coding. In other words, it may get the mail, but that doesn't mean it can read your letter.
To make system integration easier, Tektronix completed the standard by defining codes and formats that specify the syntax and coding of device-dependent messages. Our goal was to create coding that was simple and unambiguous, that used common commands among similar devices, and that featured simple and easy-to-remember mnemonics. These logical conventions are designed into every Tektronix GPIB product. Tech codes and formats not only make tech-to-tech interfacing easy, but they greatly simplify the integration of any tech product into any system. The 11000 series continues Tech's focus on operator convenience. They use common data formats and commands for both interfaces and add features to aid debugging and system integration.
Let's take a look at the bus standard itself. First, to straighten out any possible terminology confusions, let's establish for our purposes that HPIB equals GPIB equals IEEE standard 488 with both 1975 and 78 revisions. And in fact, the European IEC standard 629 is functionally identical but uses a different connector. Fundamentally, we're talking about an interconnection standard for small to medium-sized instrumentation systems. IEEE 488 is a mechanical standard, an electrical and functional standard, but not an operational standard. It defines nothing about the operation of the devices on the bus other than their very fundamental interaction with the interface itself. Here's a standard GPIB cable with connectors. The connectors can be stacked to interconnect multiple devices as you wish. The maximum total cable length can be up to 20 meters with at least one standard device connected per 2 meters of cable. 15 devices are the maximum for the bus, one of those normally being the controller. At least 2/3 of those must be powered up at any given time. Each device has a unique address on the bus between 1 and 31. Normally that is set by switches on the rear or inside the instrument itself. Here's an additional level of detail on the bus. Let me say that you don't really need to understand this detail to be able to successfully assemble and operate systems, but it may help your understanding in depth. First, the bus is made up of 24 wires, 8 of which are grounds, 16 are active wires. The bus actually consists of 3 buses. There's a 5-wire management or control bus, an 8-wire data bus, and a 3-wire transfer or handshake bus. All the voltage levels are TTL compatible and negative true. That is, a voltage near ground is a logical 1, a high voltage is a logical 0. Data on the bus is sent as bit parallel byte serial, a sequence of 8-bit bytes with the 3-wire handshake bus assuring that each byte is accepted before the next is sent. IEEE 488 defines 10 functions to describe the characteristics and compatibility of a device on the bus. You'd normally find an instrument's compliance with these functions described in the instruction manual of the instrument. The functions are source handshake, the ability to lead a byte-by-byte transaction; acceptor handshake, the ability to receive such a transaction; talker, the ability to talk on the bus, that is, put bytes on the data bus; listener, the ability to accept data from the data bus; service request, the ability to interrupt the controller to ask for service; remote local, the ability to be placed under either remote control or front panel control; parallel pole, the ability for up to 8 instruments to simultaneously tell the controller whether they just requested service; device clear, the ability to be initialized to some predefined condition. Device trigger, the ability to start some basic operation upon command of the controller. And controller, the ability to assign devices as talkers and listeners. A device need not fully implement all of these functions to be useful, and in fact, very few devices do. A minimum compliance would be acceptor handshake and either listener or talker. If talker, source handshake would also be required. To solidify these concepts, let's think about some real-life instrumentation examples. A device like a printer might very well be listener only with acceptor handshake. It takes data from the bus, prints out a paper record of it. If the printer designer also wanted it to sense its paper supply and notify the controller when it runs out, then he would also need to implement SR, service request, to interrupt the controller, plus talker and source handshake functions to send some sort of out-of-paper message when the controller services the service request. For another example, a measurement instrument, like a digital voltmeter, can be talk only with source handshake. Now, with that capability, it would talk all the time. It could be connected to the listen-only printer to make a very simple data acquisition system. To be useful with other instruments and a controller in the system, it must also have acceptor handshake and listener capability so that it can be made to talk on command. These would also be required if it's to be programmable so that the controller can tell it to switch functions or range. And if the DVM needs to notify the controller of an overrange condition, it must also have service request capability. Note that GPIB does not necessarily mean programmable. Talk-only voltmeters or printers, data loggers, listen-only could also be IEEE 488 compatible, but not programmable. Conversely, a programmable instrument is not necessarily IEEE 488 compatible, though if it's been designed during the past 5 years, it's very likely that the designer chose IEEE 488 as its system interface. The GPIB is an asynchronous bus. It's capable of speeds up to 1 megabyte per second with short cable lengths, 250 kilobytes at the full 20-meter length. However, the actual transfer rate is determined by the slowest listener involved in any particular transaction. The talker cannot put another byte on the bus until the slowest listener signifies that it's absorbed the previous byte. Various devices may be listeners during some transactions and idle during others. IEEE 488 defines only interface functions, communications between the GPIB interfaces of the various devices. Device-dependent messages are completely up to the discretion of the device designer. These interface messages can be subdivided into uniline and multi-line messages. Uniline messages are sent by asserting one of the lines of the 5-wire management bus. Multi-line messages are sent by asserting the ATN, the attention line of the management bus, then putting a specific 8-bit byte on the data bus. Some multi-line messages are universal and are implemented by all devices on the bus. These include commands like untalk, unlisten, serial poll, enable. Other multi-line messages are addressed only to specific instruments listening at that time. These include messages like selected device clear, group execute trigger, and go to local. No other types of messages are defined by IEEE 488. Thus, no definitions in the standard pertain to the form in which measuring instruments ship out data or the form in which commands have to be sent to programmable instruments. Whenever attention is not asserted, the 8-wire data bus may be used in any way at all as far as IEEE 488 is concerned. Thus, the fact that several devices are IEEE 488 compatible does not mean that they'll communicate. A telephone system analogy is a good one. IEEE 488 compliance ensures a link from device to device, just as dialing the proper number ensures a connection between specific telephones. But if one user only speaks and understands English and the other only French, no communication will take place. Similarly, IEEE 488 compliance will connect two devices and handshake bytes between them, but the bytes may be totally meaningless to the listener. We'll talk more about this problem as we move beyond GPIB in a few moments. One of the most important concepts in IEEE 488 is the service request, SRQ, and the polling methods used to handle the requests. The service request is the GPIB-defined method for a device to request service from the controller. This technique is often referred to as an interrupt. The SRQ line, which is one of the 5 lines of the management section of the bus, functions as a wired OR. If any device on the bus asserts SRQ, that sets the line true, and the controller knows that some device needs service. It doesn't know which device until it conducts a poll. IEEE 488 defines 2 polling techniques, serial and parallel. Serial polling is implemented in many more GPIB instruments than parallel polling, but both are found. In a serial poll, the controller addresses the instruments on the bus one at a time, asking each if it asserted the SRQ line. When it finds that device, it extracts a status byte from the device which tells what the device wants. Extracting the status byte also causes the device to remove its assertion of the SRQ line. The status byte definitions are not set by IEEE 488. The device designer is free to use this byte in any way he wants to mean something like, I've just been powered up, or I've just run out of paper, my data register overflowed, I just completed a measurement. In a parallel poll, up to 8 instruments can be polled at one time by each of them controlling 1 bit on the data bus. The controller can thus poll more rapidly if the instruments implement parallel poll, but the single bit cannot convey any more information except I'm the one. Further interrogation then is required to find out why the SRQ was asserted.
The 11,000 series GPIB characteristics are set through their interactive menus.
On the 11301 and 302, start by selecting the utility menu. Then touch GPIB. To change the device address, touch the up or down arrows to increase or decrease the number. Specify the message terminator by a touch. Although EOI is standard, some controllers also require a line feed character. If you wish to monitor messages with the debug feature, select CRT for display on the scope's CRT or RS-232 for transmission to a remote terminal. Other parameters can be sent by GPIB commands.
To set up the 11401 and 402, select the Utility menu and then touch GPIB Parameters. Then specify the mode, address, terminator, and debug selection by touch.
The 2445B, 2465B, 2467B family of real-time scopes are completely programmable and can be equipped with a GPIB interface to communicate over the GPIB bus. We will set the scope up to operate over the GPIB bus and then verify its settings. The GPIB parameters we need to set up to enable the scope to communicate over the bus are address, terminator, and mode. These are the same basic GPIB parameters that must be set for any instrument to communicate over the GPIB bus. The GPIB firmware switches are accessed through the diagnostic menu system. The diagnostic mode is entered by pressing 3 front panel buttons simultaneously, which brings up the diagnostic menu on the display. The 3 buttons are Delta V, Delta T, and the trigger slope button. The address is set by calling up the diagnostic menu for GP Exercise 11 by using the Trig Mode switch to scroll through the exercises. Once GP Exercise 11 is accessed, press the top of the Trig coupling button to see the GP Exercise 11 submenu. After the desired address is set, the down trigger coupling button is pressed to set the address and return to the first level menu. The end of message terminator and talk listen mode selections are made with the menu contained in the GP Exercise 12. We access GP Exercise 12 by pressing the top of the trig mode button one time. We first select either EOI or LF to be the end of message identifier. This is done by pressing the trig mode button. The display will alternate between the two choices at each push of the button. Next, we will use the trig source button to select either listen only or talk listen. In normal operation, we would want to send commands and inquiries to the scope, and the scope would be sending responses to those communications. So the scope must be both a listener and a talker, and talk-listen mode would be selected. The talk, listen, and EOI modes are set by pressing down the trig coupling button, and the display returns to the main diagnostic menu. We have finished the GPIB setup and can now exit by following the menu instructions to press the AB trig button to exit the diagnostic menu and return to normal scope operation. This is a 2440 digital oscilloscope. It is also completely programmable and has a GPIB interface as standard equipment. The first level GPIB menu is brought up on screen by pressing the Output button located in the front panel Setup section. The next selections are made with the display bezel buttons. Press the bezel button under the Setup menu to bring up the GPIB address menu. The address is set by pressing the bezel buttons below the up or down arrows. The up arrow increases the number and the down arrow reduces the number, one increment for each press of the bezel button. This finishes setting the 2440 GPIB address. There is no provision to back up in this menu, so we must return to the main menu by pressing the front panel Output button to access the Output menu, and then select Setup to re-enter the Output Setup menu to select Term. The Term submenu has two selections with the underline showing the current selection. Move the underline by pressing the bezel button under the menu item desired. EOI is the method TEC specifies in their codes and format standard. LF EOI will allow you to communicate with devices that use either EOI or LF. Return to the Output Setup menu by pressing the front panel Output button and then pressing the Setup bezel button. Select Mode from the Setup menu to access the Mode submenu. Remember that the underline indicates the current selection. The three GPIB modes we want to consider are T only, talk only, L only, listen only, or TL, talk listen. We will be sending and requesting information from the 2440 over the bus, so we would select Talk Listen by pressing the bezel button under that menu item. We could clear the screen with the Menu Off Extended Functions button, or if we wanted to quickly check the status of the GPIB settings to verify our setup, we could return to the main Output menu. Press Output and then select Status. Now our setups are underlined and listed at the top of the display. The remainder of the setups are advanced GPIB parameters not covered here. Exit the menu and return to normal scope operation by pressing the Menu Off Extended Functions button below the display. The GPIB parameters that must be set to allow the 2230 to use the GPIB bus are the same as the other scopes we've seen. Those parameters are address, terminator, and mode. On the other scopes, the GPIB switches were called up with soft front panel controls, and selections were from screen menus. The 2230 uses a block of hardware switches to set those GPIB parameters. Note the switch nomenclature. The bracket identifies the portion of the switch block that sets the scope's GPIB address. The legend on the bottom of the switch shows the open, 0, and closed, 1, positions of the individual switches. The top 5 switches are weighted to set addresses in the range of 0 to 31. The GPIB address of 5 will be set by selecting the 1 side of switch numbers 1 and 3. Switches 2, 4, and 5 will all be at 0, making the total value of all switch closures 5. By taking the sum of the first switch with a weight of 2 to the 0 power, which equals 1, and the third switch having a weight of 2 to the second power, which equals 4, we have a total of 5 set into the address switches. There are 2 methods of selecting the GPIB terminator. Switch number 6 selects one choice of terminator. If the 0 side of the switch was selected, that would set EOI only, which is the Tech Codes and Format standard. The 1 side of the switch allows both EOI plus the other method of line feed carriage return to indicate the end of string. We will set LF or EOI by placing switch 6 in the 1 position. The listen function is controlled by switch 7, with 1 selecting listen only. The mode we want to set is talk listen, so the switch would be set to 0, or listen only off. The talk function is controlled by switch 8 with the same setup as switch 7. The mode we want is talk listen, so the switch would be set to 0, or talk only off. This finishes setting up the instrument's GPIB parameters. Now connect the GPIB cable. In this example, we have made the following setups: address 5, terminator LF EOI, mode talk listen to establish communications with the controller. These same GPIB settings were made with the 11K and the 2400 series, except that this time it was done with hardware switches rather than the soft controls and screen menus. Now let's look at using the GPIB to obtain a hard copy output from one of the 2200 series of digital scopes. The setup is started by referring to the 2230 applications section of the HC100 manual for the information on the interface requirements. Both the 2230 scope and the HC100 use hardware switches to set the GPIB parameters, and the application section of the manual will provide the details needed to set these switches. The switch map will show the on or off, or 0 and 1 positions of each required switch. The HC100 setup map for interfacing with the 2230 indicates that the first 2 switches must be in the on or selected position. The HC100 will be set up first. The first 2 switches must be in the selected or down position according to the information decal on the cover. The HC100 plotter rear panel mounts the GPIB interface connector and GPIB setup switch. The first 2 switches, numbers 1 and 2, are set in the on or down position, and the remainder of the switches are to be in the up or unselected position. This completes the HC100 GPIB setup. We will use the GPIB port and cable to connect the plotter to the 2230. The setup map indicates that switches numbers 6 through 10 are required to be set according to the map to communicate over the GPIB bus to the HC100. The map shows that switches numbers 6 and 8 must be in the 1 position, and that switches 7, 9, and 10 must be in the 0 position. All other switches are don't care and can be in any position. We will set the 2230 GPIB switch to match the setup map. Switch number 6 controls the EOI or EOI LF selection. HPGL uses LF or line feed to communicate over the bus, so EOI LF would be selected. Press on the right side of switch 6 to select 1 or EOI LF. Switch number 8 controls the talker mode of operation. The 2230 will only be sending control and waveform information to the plotter. It will not be receiving any communications from the HC100. Setting this switch to 1 selects the talker-only mode. Switches 7, 9, and 10 are not selected. Switch 7 selection would be to set the listener-only mode. Switches 9 and 10 at 0 set the scope's HPGL auxiliary mode. This completes the 2230 GPIB switch setup. The 2230 plot menu is used to set up the waveform output. The plot function is located on the first level menu. This is an HPGL plotter, so the format menu must have HPGL selected. The plot is started by selecting Start from the plot menu and pushing the cursor select button. We've seen that the 11K series scopes can drive a dot matrix printer directly. Now let's take a look at the hard copy capability of the 2200 and 2400 series over the GPIB bus. For this demonstration, we will use the 2440. The 2430A or the 2432 would work the same. These instruments can drive hard copy devices directly over the GPIB with no controller required. The hard copy device is the TEC HC100 plotter using HP graphic language. The HC100 setup for a GPIB interface with the 2400 series digital scopes calls for the first 3 switches to be selected or in the down position. This completes the HC100 setup. Connect the GPIB cable from the plotter to the scope. Now the 2440 must be set up for using the plotter. The GPIB output menu is brought to the screen by pressing the output button. There are several levels of this menu, and these various levels must be accessed to set the scope GPIB parameters. The next level menu is accessed with the setup selection, which brings up the GPIB setup menu. Press Mode to bring up the Devices menu. The underline indicates the current device selection. Press the bezel button under HPGL plotter to set up the HC100 interface. This is the generic GPIB driver for all plotters that employ HP graphics language. Selecting Setup in the Devices submenu brings up the menu that controls the details of the plot. The operator can decide to plot or not plot details like the graticule, text, or parameter settings. US and international size variations are accommodated with the US A4 selection. This completes the plotter setup. Press the output button to return to the main output menu to begin the plot. Press the plot button to start the plot. Note that the menu changes from plot to abort when the plot begins. Once the 2440 has been set up to plot with the HC100, only the main output menu must be accessed to initiate the next plot.